Hello, welcome to Single Phase System Tutorial 1. Today I'm going to show you how to solve a mass balance problem using ideal gas law. So we have examples. This is the first example. Okay, let's look. What do we have here? We have a stream of air which contains 21% mole of oxygen, 70 mole% of nitrogen, is flowing at a rate of 30 kg per hour, is mixed with a stream of carbon dioxide. The carbon dioxide enters the mixer at a rate of 50 meter cube per hour at 130 degrees C and 1.3 bar. Determine the mole fraction of CO2 in the product stream. So in this question, we have one stream, air, mixed with a stream of CO2. So we have two streams going into a mixer and we have one product out. And the stream of air goes into the mixer at 30 kg per hour in mass flow rate 30 kg per hour. CO2 enters the mixer at a volumetric flow rate of 50 meter cube per hour with a pressure at 1.3 bar and temperature 130 degrees C. So we are asked to find the mole fraction of carbon monoxide in the product stream. After we get the question, the first step is we draw the process flow diagram for us to understand the question better. Okay, so we have a mixer and then we have two stream of feed. We have one stream of feed which is air, which with the mass flow rate 30 kg per hour. Okay, and then we have a volumetric flow rate of carbon CO2 equals to 50 meter cube per hour. And then we have one product out. Since the question wants you to find in terms of mole fraction, so we have to convert it everything, whatever inputs that we have, into number of mole or mole flow rate. Okay, and then we know the pressure at the CO2 pressure and the information at this line is we have P equivalent to 1.3 bar and T equivalent to 130 C. So if we have this information, it's easy for us to convert it to molar flow rate because we can use PV equals to nRT. To find mole fraction of carbon dioxide, we need to know the molar flow rate of the product stream. To know the molar flow rate of product stream, it is equal to mole of air that goes in plus mole of carbon flow rate. Molar flow rate of the product stream will equal to molar flow rate of air that goes into the mixer plus with the molar flow rate of carbon dioxide that goes into the mixer. Then you will obtain the molar flow rate of the product, or this one I noted as total molar flow rate of the the product stream. Okay, to find molar flow rate of air is easy because this system is ideal gas law, so we'll just do this like this. So molar flow rate of air is equivalent to 30 kg of air per hour. Just divide by the molecular weight of air, which is 25 kg air per k mole. So you obtain number mole of air 1.03 k mole of air per hour. So then you obtain this molar flow rate of air. Okay, now you need to find the molar flow rate of CO2. Here, what you are given is the volumetric flow rate. So we have to convert this into molar flow rate using PV equals to nRT equation because it is an ideal gas state. So we use PV equals to nRT. We just rearrange, so we obtain the number of the molar flow rate of CO2 is equivalent to PV. This is the volumetric flow rate. Yeah, sorry, I forgot the dot here. Pressure times volumetric flow rate divided by RT. Since we are given V, the volumetric flow rate, in terms of M3, meter cube per hour, so it's better to use this gas constant with this value to get your mole per hour answer. Okay, so now what is our P? So in order to use this equation, we have to convert P because we know our gas constant is in Pascal, but the information that we are given is in bar. So our P has to be converted from bar to Pascal. So what we do is we times 1.3 bar with the conversion factor. You can find this conversion factor at the first page of your textbook. So you know that to get Pascal, because we have gas constant in terms of Pascal, we convert it using this unit, conversion unit. We'll get 1.3 bar is actually 130,000 Pascal. Okay, for temperature, because our gas constant requires Kelvin, so we have to convert from Celsius to Kelvin, so we obtain 403 Kelvin. So now we can start solving and get our molar flow rate for carbon dioxide. So now we just use this equation, so we'll get the molar flow rate of carbon dioxide. So we know our P is this value here, we put our P. We know our volumetric flow rate is 50 meter cube per hour. Okay, divided by R, this is our R, put it here. Okay, this is our R. And then divide with T. Our T is 403 Kelvin here. So when you do the calculation, you get 1940 mole per hour of carbon dioxide, which is equivalent to 1.94 kmol per hour. I change this mole to kmol because I want to make it similar to kmol air just now. Okay, so to find the total flow rate of product here, so this is the equation just now. So you add the molar flow rate of air plus molar flow rate of carbon dioxide, then you'll get the molar flow rate of the product. Sorry, still I forgot the dot here. Should be molar flow rate of the product. Okay, right. And then you already have the molar flow rate of the whole product line. So to find mole fraction for CO2 is not difficult. So you know the formula is molar flow rate of carbon dioxide divided by molar flow rate of the total product line. Then you obtain the mole fraction of CO2 at the product line. So you obtain here when you calculate 0.65 kmol CO2 per kmol. That's it, tutorial number 1.